Alright, are we live? Hello, 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 hello. Just taking a moment before we get started. Alright, so let's get into it. So, bulb switcher. Let's see how we do. There are n bulbs that are initially off. You first turn on all the bulbs, then you turn off every second bulb. Oh, I know this question. I think I know this question. This is an interesting one. This is I've seen this a few times now. Oh, this is a really, yeah, hold on, wait, let me get a lot of downvotes. I think, if it's what I think it is, it's a really interesting question. And it's kind of a copy of another question. It's called, there's a ninja's question where every ninja stabs the ninja, or if you're familiar with, or is it ninjas or samurais? That's what they would be, samurais. So every samurai, you have a circle of samurais, and every samurai takes out a sword and kills the samurai to the left of him. Right, and you give every samurai, before you kill anybody, you give a number to every samurai, right? 0 through n, or n-1, or 1 through n. Every samurai kills the samurai to the left of him. That's one round. Second round, every samurai kills the one to the left of him. Second round. Third round, do it again and again and again. There'll be one samurai left. There should be one samurai left. And what's the index of that samurai? Is the question. I think it's not the person to the left of him. It's one more over, I think, something like that, or it's every other samurai kills the one to the left of him. I'm sorry, it's not. He doesn't kill the one to the left because then everyone would die in one shot. Kills every other samurai kills the one to the left of him, starting from the 0, 2nd, 4th, etc., or 0, yeah, 0, or 1st, 3rd, 5th, etc., in sort of the circle. Right, that's what it is. Every other one stabs the guy to the left. So, yeah, you get a. That's an interesting question. What's really neat about that question is there's actually a formula to find the index of that samurai in a constant time. There's a closed form solution. It's a very interesting problem. I think it's probably the same problem. Third round, you toggle every third bulb. No, it's not the same problem. This is slightly different, but it's an interesting question. This is probably be an interesting one. That one I don't remember what the solution was. There's a way to derive it, or to kind of think about it. You can kind of derive the answer. There's like a formula, and then you can actually prove it. In the third round, you toggle every third bulb, turning on if it's off, or turning off if it's on. Oh, interesting. Okay. So you turn off every second bulb, and you toggle every third. For the ith round, you toggle every I bulb. For the nth round, you only toggle the last bulb. Return the number of bulbs that are on after n rounds. Round 1, round 2, round 3. Okay. 0, 1, and is between 0 and 10 to the 9th. So I think this has actually a closed form solution. I forgot how to do this one. I've seen this one too. I would start. This is like a classic interview question too. I've seen it multiple times, but I don't remember it. It's been so long. So this is like, we're going back, I don't know, maybe 6 years ago, possibly 6 years ago, 7 years ago, when I looked at this problem. So we'll say, I don't know what to even draw. I kind of want to draw something like this. We'll do like 10 of these. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, oops, 9, and 10. Okay, so we have 10 of these 10 here. We're going to save this. Save that off. Push that off to the side to kind of save it for you to use. Now what we want to do is they're all on initially, right? So we'll say, I guess we'll be just put a dot if they're on or off. All on, and then half of them are off after the first round, right? Or every other one you turn off. It's not half of them. 1, 2, 3, 4. Right? And then every third one you toggle. So this is pretty interesting. It's pretty interesting. The toggling is basically like the XOR function, right? If you recall, we went over XOR functions quite a bit recently. And so you can actually create kind of like a I mean, there's a few things you can do here. It's pretty interesting. So let me think about this. How do you? There's this is an interesting problem. I'm just gonna say it's an interesting problem. We'll do like 4 iterations, and then I'll talk about like the different things to analyze. So every third you toggle. So third, fourth, fifth, sixth. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, did this? We'll do one more afterwards. Is this only 9? 1, 2, 3, 4, 6, 7, 8, 9. How did I do that? How did I mess up before? I wanted to make 10, I made 9. I did that before too, I miscounted. But that's okay. And now we do 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Right? Now what you'll notice is you basically can make a count for each position and say, okay, this position is divisible by 1. But it's not divisible by anything else, right? So you have you basically can count how many times these things are divisible by these different values. So 1, 2, 3, and 4, and then you could take the number that it's divisible by and take that modulo 2, and that'll give you whether or not it's on or off. Because if it's divisible by 1, it'll be visited once. If it's divisible by 2, then it'll be visited by 1 and by 2. Divisible by 3, same thing. So you can actually decide, like, there are a few things, like, so you can actually walk through the whole algorithm over an array, and then you would have your count, which literally is like just counting, right? You would sort of figure out at each point. But there's something kind of more interesting going on there, because you're looking for numbers that have basically these are the divisors of a particular number, right? So if you look at, and divisors are always smaller than the number of iterations. I think, how many iterations will you have? Let's see. N is between 0 and 10 to the 9th, and we're looking for, I guess I could be anything, right? Doesn't give you a bound on what I is. I was going to say if I is kind of small, then, well, There are a few things to consider here. There are a few things. Just thinking. I was gonna say you could take the number of divisors, but that doesn't really make too much sense. So one of the things is that the n being 10 raised to the 9th, that's a billion. That would be really awkward to put into an array and operate on. So we kind of do need to find like the more efficient solution to this. We don't really have a lot of options, but obviously dumping it into an array and just literally and like simulating the algorithm. The analog to that would be actually finding out all the divisors for each of those numbers. It's actually easier probably to simulate than it would be to actually find each of these terms, their divisors, and then count the number of those divisors that are less than I, and take that modulo 2, right? So it's either 0, 1, 0 being it's off and 1 being on. You have so you got to come up with a better way. I want to say something about XOR functions, but I don't think it works that nicely here. Now, could you? No, I don't think so. But I was just thinking maybe somehow we can fit in game theory in here. Use the SG theorem. Somehow use the SG theorem to. If we called this a game and we said, the first player moves. Every ith, or the first player moves every I positions. The second player moves every second position, and so on, right? The ith turn moves I positions, and then the player who's I guess it makes the last move, wins or loses. I think you need to have normal play and impartial, and it has to be a player can't move or a player basically a player can't make any more moves. I don't think that works, right? Because this doesn't really have that same property to it. It's not really, it's more just a raw calculation. But the question is, Howdy Duty. How do we we basically want like a closed form solution. So for 1 we got 9, for 1 we got 9, all 9. For 2 we got 1, 2, 3, 4, 5. It looks like half of them, 9 minus 9, we had 9 minus half of 9, 5. Then we had 1, 2, 3, so 1, 2, 3, 4. We had 4 left, which was like the 5 previously, and we said the positions matter, right? We said we're not going to affect 1 by 3, but we do affect actually exactly this third value, and this 6th value actually gets toggled back on. So we remove 1 and add 1, and then finally remove 1 over here at the end, which is sort of like, it's 9 minus 4 minus 2 plus 1, right? Because it's 4. Okay. And then finally, we have 4, we add 1, and we add 5, 6, 7, 8, we add 2. We actually get back to 6. End up at 6. Let's see if we kept going, what would happen. It's kind of curious. So we said this is 1, 2, 3, 4. We say 5 now. We would go 1, 2, 3, 4, 5. Excuse me, toggle that back off. 1, 2, 3, 4, 5. 6, 7, 8, 9, right? So that would be, then goes to toggle that back down to 5. And then 6. One, 2, 3, 4, 5, 6. We toggle off to 4. Back to 4. See that the last values actually would start to flip again. 7. And then 8. Seven, 8, so we get 4, 3, 2, and then finally you have 9, and it goes back. So actually, there is a bound on I, right? I is between 0 and n. Let me go back to 3. So I take that back. So I is less than or equal to n. Right, it must be, because after that, beyond that, it's meaningless. Right, it doesn't change, becomes idempotent after that. Oh, excuse me, n rounds. I'm sorry, I didn't see that. I missed that. So it is actually after n rounds. So it is supposed to be every. Oh, I'm sorry. Okay, this actually should be easier then, because then it's yeah, it actually is what I was saying before about the number of divisors. That actually works then. So there is a way to I think to calculate that in general, to figure out the number of divisors, how many of them are odd, how many of them are even. So let me think here. So every number has two divisors at least. It's one in itself, right? So that's the first thing. Except 1, obviously. Obviously 1 is just 1. So 1 is always there. Anything else is going to have 1 in X. So 1 and 2 is never going to be, that'll always be 0. 3 will always be 0. 4, 1, 2, 4. That's a 1, right? There's divisor for 2. Now, composite divisors don't really do it for us, do they? Well, they could be triple composites, right? They could be three numbers, 3 divisors. It really is the number of divisors, right? Like that's ultimately what we're looking at. However, the problem with that is that that's O of n times square root of n, and we're looking at 1 billion for n. So that's a little too expensive if you count the divisors as I described. It's a little too much. Yeah, we probably can't even do O of n. We probably have to do better than O of n. O of n for 1 billion is still pretty expensive. So there's a way to do this, though. I think I'm pretty sure there's a closed form solution for this, but I don't remember it. One, 2, 3, and 6. So 7, 1, 2, 4, and 8. Let's see if we can find one that's got 1, 3, 9. It's got like 5 divisors or something. 1, 2, 5, 10. 1, 11. Oops. 1, 2, 3, 4, 6, 12. Right. 1, 2, 3, 4, 6, 12. 1, 2, 3, 4, 6. Yeah. 13. I'm trying to find one that has like a few divisors, but I guess 12 kind of counts. Well, 12 only has like 2 prime divisors, right? The thing with the divisors is that I want to say the totient function can be used here. I want to say that, but I don't know. I don't actually know. Basically, every number has some 2 raised to the alpha sub 1, 3 alpha sub 2, and so on. You know, some p sub I, alpha sub I, and so on. And the deal is, with these things, the number of divisors is actually going to be the product of all of these. If you take these values, alpha sub I, it's actually, yeah, it's the number of divisors, not the set of divisors, but the number of them, which is to say this is equal to some alpha sub I for all I, alpha sub I plus 1 times, right, all the other alpha sub i's plus 1. Is it plus 1? Or is it just... let me just see. Let's see, 12 would be... I don't know if that's right. Hold on. 12 is 2 to the second times 3 to the second, right? What you get? 1, 2, 3, 4, 5, 6 divisors. This would give us 9. That's not correct. I want to say it's actually something like more like no. Yeah, it's pretty close to this. Why is it not this? Well, you could have 0, 1, or 2 of each of these. And any combination will give us a different number, right? So 2 to the 0, 3 to the 0 is 1, 2 to the 1, 3 to the 0 is 2, 2 squared, 3 to the 0 is 4. Excuse me. 2 to the 0, 3 to the 1, 2 to the 1, 3 to the 1. Oh, that's why, because there's some overlap with these. No, that's not, no, that's fine. It's 0, 1, 2, 3, 1, 1, 2, 3. No. All right, no, we're fine. 2 squared, 3 to the first. 2 to the 0, 3 squared, 2 to the first. See, that's why. Oh, that's why. Yeah. No, I'm right. I'm fine. This is not, because that's the wrong number. This is a 1. This is 4 by 3, not 4 by 9. That's why I'm getting. Yeah. No, this is right. I was like, I'm pretty sure I have the right idea here. That would give us 3 by 2, which is 6, which is exactly the number of. Yeah. Okay. Now what we want to say is. This is basically the sum of, for all x, the size of d sub x modulo 2. And now the thing that's interesting about this, not modulo 2, I'm sorry, modulo 2, the sum, yeah. No, that is what we're looking for. Yes. Each one of those modulo 2 added together. Interesting. Yeah, that's a good question. Like what? So, I guess one thing you can take a look at is if you take this alpha sub I plus 1 mod 2, that actually ends up being, let me resize this. That actually ends up being each of these mod 2. Which means actually a change in any of these prime numbers will increase your will toggle your value. So actually what we could do is we can compute this in logarithmic time, at least, by taking the number of prime numbers that are less than or equal to n. So we can use a sieve of Eratosthenes to find out the number of prime numbers and that we're going to need. Sieve of Eratosthenes. And the reason for that is we know we're 0 unless we get some prime multiple, right? So the prime numbers themselves we don't really even care about. So we don't need all of the primes between. Actually, none of the prime numbers will even matter. We can skip all of the prime numbers because all of the prime numbers there's it's just alpha sub I plus 1, which is alpha sub I is 1 plus 1 mod 2 is 0. So we don't care about any of the prime numbers. We only want to find the prime numbers to figure out how many multiples we're dealing with to toggle. And excuse me, basically, how many numbers do we start with, and then what do we remove? Or how do we want to do this? How do we do this? Well, basically everything is initially off, 0, and then if it's a multiple of a prime number, then it becomes a 1, and then if it's a multiple of another prime number, then we would toggle it back. I guess we want to see, the tricky thing is no, this doesn't help us as much as I think it does. This doesn't really help us because it's not logarithmic, because just counting how many numbers are multiples of 2 or some prime number isn't really enough. Yeah, because we can't just have a huge array of numbers that we're counting. Like, that doesn't work. We need something a little more, something better, I guess. I don't know, man. I don't know. What do we do? What do we do? There is this notion of like the inclusion-exclusion principle. So in theory, we could compute the inclusion-exclusion values for each newly introduced multiple. However, can be a little bit complicated. Can be a little bit complicated. Even that's kind of confusing too, because you're dealing with, like, what do you do with like 2 cubed, right? If we just consider the multiples of some prime number, that doesn't really, we're trying to, I guess, construct this value, whatever this is, which is kind of hard to do. A little bit challenging, I suppose. I want to go take a look at the totient function quickly, because I think the totient function might be useful here. You kind of need to know a little bit about, number theory in order to use the totient function. Yeah, relatively prime. They don't contain any factor in common. One is counted as being relatively prime to all numbers. Less than or equal to and relatively prime to a given number is called a totive. Number of totives, or a totative, right? Sorry, not a totive. Totative. Totative. Number of totatives. 8 totatives of 24. So the totient is 8. Yeah, the totient function has an interesting formula, right? If you knew the primes of n, it looks like this. Divisors of d of n via totient of d equals n. Totient function is connected to the Mobius function through the sum. The interesting thing about the totient function, I don't know if the totient function is useful here. That's kind of what I'm looking for. I don't know. This question that we're looking at is not supposed to be this difficult. This is actually like I said, it's a pretty standard question that you ask. I just don't remember how to do it. I also don't remember, I don't remember even like the path of logic to solve it, but this is like a very standard question. Very typical interview question, but here I am. Here I am, not remembering how to solve it after all. Is an equivalent expression would be asking how many numbers less than or equal between 1 and n inclusive have an odd number of divisors. That's another way of expressing it. Actually, oh, no kidding. This is a very, Oh, I forgot. I know exactly what this. No kidding. That's very clever. Is this what I think? Hold on. What do we get? Oh man, this is why it's so. You gotta be kidding me, man. Is this? Let's see. How do we do? Oh, look at that. Is that what it is? Is that what it is? Just a square root function? Let's see. How do we do? Let's see. Oh, look at that. Come on, man. It's a freaking problem. Tisk, 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 tisk. At least we're faster than everybody else. I forgot about this problem. This problem, it's a cute problem. It's a funny problem. That's... come on, man. This freaking problem. So I'll explain. So this, yeah, it's really... Okay. Yeah, whatever. Whatever. Alright. Whatever. So... Unbelievable. This problem is, it's a good one. This is a good one. There's actually a function to calculate the square root of n that's better than this. This works fine because n is relatively small. You don't have floating point errors, but if you had floating point errors, there's actually a function to calculate the square root of n. And I kind of want to go into that. That's using the you can use what's his name's hill climbing algorithm. It's called, it's not from Matt, it's another guy. What's his name? Yeah, I'll explain the answer in a moment. It's Newton's root finding algorithm. And what you're going to do is you're going to use Newton's root finding algorithm. Yeah, so, okay, so, by the way, the explanation, really simple, is that you're looking for, count the number of numbers less than or equal to n, between 1 and n inclusive that have an odd number of divisors. Well, if you think for a moment about, if you look at these numbers, you notice something, you realize, wait a minute, the odd ones are the ones that seem to be perfect squares. And you say, wait a second, why would that be? Well, for every number, if it's not a perfect square, if there's a divisor a, then there's another divisor b that's basically n over a, right? Both of those are integers. They come in pairs. Every divisor has a pair. The only time that a divisor doesn't have a pair is when it's a perfect square, when it is itself a divisor, right? When n over a is equal to a, which is n is some a squared, which is n is a perfect square. How many perfect squares are there that are less than or equal to n? Well, if you try to count them, you have 0, 1 squared, 2 squared, 3 squared, 4 squared, etc., 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 all the way up to some value k squared that's greater than or equal to n. Well, that's exactly k would be the number of perfect squares. K is greater than equal to, k squared is less than or equal to n. That means that k is less than or equal to the square root of n. And in fact, it would be the square root of n. Although the only reason it would be less than n is because the next perfect square would go beyond n. So this is just the square root of n. That's it. That's the whole. And you can calculate the square root of n a little bit more efficiently than this using Newton's root finding algorithm, which I don't remember exactly. It's the last time I did this, I kind of messed it up. Because you got to kind of Newton-Raphson method, numerical analysis. Successively better approximations of the roots, real valued functions, single variable function, the derivative, initial guess for root sufficient. If the function satisfies sufficient assumptions and the initial guess is close, then It's better approximation geometrically is the intersection and tangent of the graph. That is the improved guess is the unique root of the linear approximation at the initial point. Process is repeated as below until a sufficiently precise value is reached. So you want to get f of x0. So x sub 0 is an initial guess, and x sub 1 is going to be that minus f of x sub 0 over the derivative of f of x of the at f of x sub 0 or divided by the derivative of f at x sub 0, which I haven't like seen the proof of this, you know, I haven't like derived this for myself. I'm not super familiar with it, so I kind of struggle to remember this. However, this appears to be one of the ways to find a root for a function, which is useful if you're looking for perfect squares, or you're looking for a square root. Yeah, haven't really tinkered with this very much. Basins of attraction. Yeah, this reminds me of hill climbing algorithms. Hill climbing algorithms are similar. I want to say it's actually the same thing. Hill climbing algorithms are basically based. This is basically based. What do they call that? Machine learning algorithms, right? Some of them they're based off of this. Not all of them, but some of them. There's certain specific ones that are based off of basically this idea. Hill climbing to find. I don't even think they're not necessarily roots that you're looking for. Though with not necessarily looking for roots when you're doing the machine learning. You're actually looking for. It's actually hill climbing is a little bit different. You're actually looking for minimums and maximums within a graph, within a multi-dimensional function. Literally like hills, like climbing up and down gradients on hills. Okay, so what we want to do is we're looking for the root of. Since this question is like a little bit too easy, if we just use this square root. What we want is we want to find the square root of some value n. We want the root value. Where's the root of that? So it's going to be, you can do square root of some value x. We'll say square root of x. If we say okay, this is what we want to do. We want to take the square root of k, right? So we have x squared is equal to some k, right? And we want to know x is supposed to be the square root of k, right? Let's do it that way. Yeah, let's do it that way. So okay. So we have some x is the square root of k. What we want is x. We're looking for the square root of k. K is some number, right? So that means that x squared minus k equals 0. That's actually going to be, so it's a parabola like this. X squared minus k equals f of x. And we can start at k, that should be fine. We can start wherever we want. But we want to find the root of this function on the right side, right? That's pretty much, you can also start with 0 too if you wanted to. And yeah, there you go. So that's f, and then f prime of x is 2x. And so x sub n plus 1 is going to be x sub n minus f of x sub 0, or f of x sub n, which is x sub n squared minus k over 2x sub n. Is that right? Why does this doesn't feel right? Something about this doesn't seem right. Which basically ends up being x sub n minus x sub n squared. Oh no, yeah, I do remember this, right? It doesn't seem right because it's kind of, it's a little funky. It gives you x sub n minus x sub n over 2 minus k over 2 x sub n. So that gives you x sub n over 2 minus k over 2x sub n, which is a half of x sub n minus k over x sub n. Yeah. Yeah. And we want this to be basically like we want this to be more or less floating point arithmetic. And I guess we could start x at 1. I think that's fine. But yeah, we can define this lambda function. And then we can start x wherever we want, I think. We can start x at 0 too. No, you can't start, you don't want to start x at 0. That's probably the only spot you don't want to start it at. But in either case, you should end up at 0. And yeah, so we'll do that. So let's try that. Let's do auto Newton. It's going to be some numerical analysis. X, turn 0.5 times x minus, in this case it's n that we're looking for, and n. We'll do int k as well. We'll do it that way. K divided by x, 1.0 times k. Right, we just want to make sure everything's in doubles using floating point arithmetic. Yeah, using floating point arithmetic. So k over x, x minus k over x times a half, which is exactly, I think, what we had here, right? Yeah, yeah. And then, so we can take Newton, oops. And we're going to go ahead and say, while true, right, while true, we want some int val, so we'll say initial, or yeah, call it x. We'll just call it, straight up call it x. X, which is going to be 1, start off with. Let's say double, or say x equals Newton of x into n. And we'll say val, this could be int of x. If val times val equals n, return val. Else, return int of standard square root of n. Let's just return -1 for now, just to see if this works. Time limit exceeded. Okay. Interesting. So n is k, x is 1 minus this very large value times a half. We can start x out at n, I think. I think that works. What does this do? Doesn't work, huh? Really? Am I doing something wrong here? Huh. Oh, that's probably why. Yeah, it's this is why. Plus k, that's why. Duh. I thought that was, yeah, I remember that. I actually do remember that. I was thinking about that. I was like, I thought it was a plus sign or something. Time limit exceeded. Still time limit exceeded, huh? Not expecting that. Now where's that? Oh. No. Huh. Oh, that's why. Okay. I think. I don't know. I'm not sure. I don't know. It's. Am I losing my mind here? It's x sub n minus f of x sub n over f prime of x sub n. Yeah, that's fine. We just take x, make it Newton of x. We're using n and k. Why is this not working? Let's take a look at some of these. Let's just do 2. What is going wrong? One and a half. Okay. Right. Excuse me. Why does he give you 1.5? Well, it shouldn't. I think it's got. It might be this. It's definitely because of this. No, it still gives you the same. Oh yeah, okay, that's a lot better. But why? It's still really confusing. I mean, this actually should have converted this whole expression. This shouldn't have been integers. Like, that's better. That's way better. It's way closer. But now the question is... Oh, I see. Right, so the square root of n actually does need to be a double, so it needs to be something like this. It actually needs to be something like this. So what does this look like? Time limit exceeded. That's awkward. Okay. What does that give us? 2. That's good. Is it just because it's not an integer? I'm sorry, what is going on here? Why is this taking so much time? I'm so confused. Watch. Would you please explain? These are not equal to each other? Somehow these are not equal to each other. For reasons that are totally beyond me. Can we just, wow, okay. You know what you can do? How about that? How about that? Hey, there we go. Okay. That's a little bit better. Just if it just hits a what do they call that? A point where it stops looping. How about that? Oh no! Doesn't work for 0. Does this? Oh, it does say. Come on, man. Of all the test cases to miss, of all the things to miss, if it's 0, the square root of 0 should be 0, right? What do we get if we do the square root of 0? It's x squared. It should actually give you, what do we get for x? This is a half of, well, what's k? K is 0, I think, right? So this is just 0. It's a half of 1. Really, this doesn't, I think this actually should work. Let's see how we do. Oh, that goes for a while, huh? Well, that goes for a while. Yeah, 0, negative nan. Just gives up. Just gives up after a while. It's pretty funny. Doesn't really work too well in 0. We could just say edge case. funny. Is that the only one that it failed on? Yeah, okay. That's too funny, man. Nice. Nice. Alright. Neat. So yeah, I feel like a smart guy realizing what, you know, the question's asking for. Probably better off using square root of n, really, actually. But this is definitely, so definitely interesting. Definitely interesting. If you had k is 0 in this function, right, f of x equals x squared, oops, f prime of x equals 2x, we'll say, we'll call it q of x is going to be, it's basically, you know, you just apply q over and over again, right? It's going to be x minus f prime, or f, which is x squared over 2x, which gives you x minus a half of x, x over 2, which is x over 2. Which is pretty funny because finding the root, I mean, yeah, you will get to, you never actually get to the midpoint, do you? You never actually get to 0. You get very close to 0. You get within epsilon, you get in with, you know, x minus epsilon, or you get within x minus, call it r of x, the root of x. You can make, and then you get epsilon arbitrarily close to 0, right? Yeah, you can you can get x arbitrarily close to the root of x with this function. However, it's never actually equal. It's pretty funny. It's pretty funny. And so our algorithm would fail here. Interesting. Yeah, you could use this instead of the regular square root of x function. Newton's method, right? It's, I have to memorize that. It's half of quantity x plus k over x. It's really clean, you know. But yeah, that's one way of finding square roots instead of using the square root function. Just kind of neat, kind of nifty thing. Oh, this has got to be an integer, right? Yeah, it does convert to an integer. But yeah, I like that, man. It's super efficient. I mean, not just efficient, but it's like a smart guy figuring that out. All right, anyway, figuring it out again after, I mean, I've seen it a few times, but figuring it out again after that, I realized I spent like an hour on this, but like, I don't know, it's like a very, that question brings back memories. That's a question I haven't seen in a long time, and I appreciate it. It's a nifty question. It's very clever, I guess. Makes you feel smart. It's a very, like, subtle thing. Very subtle. But it just happens to work out nicely. Yeah. Oh, that problem, man. Oh, that problem. Anyway, alright. So, thank you all for watching. Talk to you soon. I think I'm probably just going to go to bed now. I might... Nah, I don't want to do another problem. I kind of just wanted to forget about my problems for a while. I have so many things that are on my mind that I'm concerned about or worried about or what have you. And yeah, I don't want to think about those things, so I wanted to solve a problem. Hopefully that was interesting. But yeah, it's counting the divisors, finding the odd divisors, and as it turns out, the numbers with odd divisors, odd number of divisors, must be perfect squares. because every divisor will have a pair, and the only time you have a divisor that doesn't have a pair is when the divisor, we'll call it A, is equal to its counterpart, which is n over A. So you have A equals n over A, which means that n is equal to A squared, which means that n is a perfect square. So yeah, and then how many perfect squares are there between 1 and n is the square root of n. So yeah, thanks again for watching. Talk to you soon. Have a good rest of your day.